In ethers, we need to first understand the type of ethers. First, we might have symmetrical ethers and unsymmetrical ethers. If you have like this is a symmetrical ether, and if the alkyl groups are different, then it is unsymmetrical ether. Okay. Next, if you have ethers on benzene, this is called anisole, or also known as methoxybenzene. Both of the names are accepted IUPAC names. Okay. Structure wise, if you notice, we have oxygen with lone pair, and R groups here. Okay. The angle between bond angle keeps increasing. This bond angle keeps increasing as R will become bulkier. If R is methyl, R is ethyl, there R is isopropyl. In that case, if this is theta 1, theta 2, and theta 3, then theta 3 should be greater than 2 than 1. Okay. So as the bulkiness increases, bond angle will increase in this case. Got it? Next. If you notice the preparation wise, first double bond, when you treat this with alcohol in the presence of H plus, Markovnikov addition will take place, H positive charge, and then alcohol will add on to that, so that makes it OR. This is how ethers can be made. Oxymercuration, demercuration, where you have Hg, OAC twice, methanol, and then NaBH4. In that case also, you will see OMe forming here. Correct? The examples typically that were asked from this area, in exam is like this, where there is a double bond here and there is an OH group here itself, and HgOAC twice was being asked. So what would happen here is, first you will get a mercury bridge, and afterwards this oxygen only will connect here like this. This is the product. So internal attack is favorable in this case. Yeah, internal attack is favorable. Lastly, if you have, anywhere alcohol within the molecule in the presence of H plus, now you will see the lone pair will attack here itself. Where there is a stable carbocation, it will attack there. Notice that a six-membered ring is formed here like this way. This is the product form. Okay. You know that Williamson synthesis and all of that, I'm not going into that. You know how to prepare, using phenols and using alkyl halides. How do we get that? Okay. I don't think we need to get into those details. Mainly, we need to emphasize on the reactions. Okay. First one is cold concentrated H2SO4. So that is if you have ROR plus H2SO4, which is concentrated but cold. In that case, only protonation will take place. No bond breaking is observed. Simply, it will form and salt formation. That's it. This is the salt form. Okay. Next one is dilute H2SO4. The minute you add dilute H2SO4, first protonation is the same, plus H plus. So first protonation will occur. And after that, because it is dilute, which means there is sufficient water present, water will hydrolyze it. It can attack on any of the R to convert into 2 moles of alcohol. Right? This is dilute. Next one is Lewis acid. Lewis acid. How does it behave in Lewis acid? If you have ROR in the presence of BF3, Lewis acid, in that case, You get ROR with BF3 plus here. Okay. Again, it will stop at this point if you do not make any reaction further. Got it? On this note, you can see 3 moles of ROR is there, and I add with BCl3. So I'll get RCl of 3 moles and boron with OR thrice. Okay. And ROR with PCl5 or PCl3, that logic will also work. So 2 moles of RCl plus POCl3. Next reaction is about cleavage by concentrated HI. If I use concentrated HI, what will happen? Okay. Again, in this condition also, I'm first using cold concentrated HI. In that case, we will get this as ROR dash plus concentrated HI. In that case, we will get it as alcohol plus R dash OH, R dash I, or Ri plus R dash OH, depending upon which one will leave. Okay. Here, let us make it more easier. Suppose uh, if I keep this groups here, R and R dash, okay, and let me write down this. If R or R dash, okay, if R and R dash, or sorry, R or R dash is either methyl or 1 degree, okay, and other one is 1 degree or 2 degree, then only SN2. Then you see only SN2, otherwise SN1. Otherwise SN1. Let me show you examples and let you know this one. See, if at all we have it like this with cold concentrated HI. Now, first protonation will happen, plus charge will come here. And now you could notice that there is CH3 present. Either it should be CH3 or 1 degree, and right hand side it should be either 1 degree or 2 degree. That's it. It cannot be 3 degree. Okay, it should be any of this. So in that case, iodide here minus will attack on this side. And that's how we will end up getting CH3I and this OH. This is the product form. Okay. Next, if you have like this, same reagent here. Okay. So we'll get 2 moles of, sorry, 1 mole of OH and the other mole of I. Yeah. Next, if you have like this O and this way, in that case, this will be OH plus first a carbocation will form and then imines will attack iodide. So this is going via SN1 mechanism. So if you have like this phenyl, this one will also form SN1 mechanism because this can give stable carbocation. So what do we get? We will get OH here and pH positive charge here, and imines will attack pH I. Okay. This is how the products are formed. I hope you understood in which case to use SN1 and which case to use SN2. Okay. In which case the reaction will not happen. See, if you have you know, anything where there is bridged position like this way, like this. In that case, if you treat with HI, in that case, we will not see any reaction happening. Okay. Phenol and phenol will also make no reaction in this case. Got it. Next is reactions with hot concentrated, hot concentrated HI. Got it. In hot concentrated HI, we expect that whatever the alcohol is forming, that will again give, that will also give away iodide. Sometimes the same terminology is also given as excess HI, excess HI, which means whatever the alcohol is forming, that will also further convert into iodide. So we can see this one will become iodide and this one will also become iodide. That's it. This is with hot concentrated cases. Okay. Next, you will see Zichel's method of identification as number of OMe groups. How many number of OMe groups are present? Okay. So imagine I have OMe group of some X groups here, and then I treat with concentrated HI and heat it. In that case, I'll get X moles of MEI. We'll get X moles of MEI. And then when you treat with AgNO3, it should form AgI precipitate of Y grams, Okay. Then you see the number of moles of AgI will be equal to X into number of moles of ethers, isn't it? How many moles of ethers are present? Number of moles of AgI will be equal to Y divided by 235. 235 is the molar mass of AgI. That is equal to X into weight of ethers divided by molecular weight of ether. That's it. So if ether's weight and molecular weight is given to you, you can directly calculate what is the value of X. Okay. So from here, X will be equal to Y by 235 into molecular weight divided by W. This is via Gisel's method. Next, using chlorine, next reaction is with Cl2 in HNO. So suppose I have ether here treated with Cl2 in dark. If it is dark, there will be very, very less amount of radicals formed. So you will get only this kind of chlorination. In fact, further Cl2 and dark, if you react, one more Cl can maximum approach at this position. But if this is Cl2 in light, Cl2 and light is given, in that case, all chlorines will get replaced. So chlorine and chlorine here, chlorine and chlorine here, and Cl, Cl and Cl here, and Cl, Cl and Cl. So you could notice that all of the chlorines will get replaced here. Okay. Next, what is about cyclic ethers? Cyclic ethers terminology name is important. This is called oxirane in IUPAC terms. It is called oxirane. The old name is to be written as 1,2-epoxy ethane. Epoxy is the wording that used to be used earlier, but not in the new terminology. In new terminology, it is written as um, oxirane. For example, in this case, so the numbering should always start with oxygen. So we have here 2-ethyl 2-ethyl, 3-methyl oxirane. That's how we will get an oxirane name. And by chance, if you have a bigger chain, then you will use that epoxy term. Like this, I have. And OH is on this set. So obviously, functional group wise, OH is supposed to be the case. So 1, 2, 3, 4, 5. In this case, you have to use it as epoxide. So 4, comma 5 epoxy, 4, comma 5 epoxy pentanol, 4, comma 5 epoxy pentanol. Okay. Preparation wise, if you notice, any double bond you have, if you treat with O2 in the presence of silver or MCPBA, okay, this would give us epoxide, epoxide, sin epoxidation. Clear? And suppose if you have a cis molecule here, cis plus MCPBA, then I'm supposed to get, because it is a syn addition, I should get erythro. Erythro means both on same side. So you can see this is how it is. This is erythro. If it is trans and MCPBA is given, in that case, we will get methyl and methyl on the opposite side. Correct? And plus and minus. It will be racemic mixture. Another one is by halogen and OH group present. This one will also give that preparation. In the presence of OH minus, this will take H plus away, and then the toxin will get connected and X minus will come. Okay. This is how we can get epoxide. Now, usually, whenever you have epoxide, the typical questions that revolve around is if you have a substitution here. So suppose if you have two methyl groups on it, okay, and if I use MEO minus Na plus, that means direct nucleophile is there. If you have direct nucleophile, in that case, the attack will always form on the less substitution side, OMe, typical SN2 mechanism here. SN2 mechanism, and that followed by hydrolysis. So make this as OH and OMe. This is how the hydrolysis will take place. Next, if you have same thing MEMGBr, correct? The product wise is it is same. So instead of OMe, this time it is Me, and with hydrolysis, we'll get this as an alcohol with Me. Okay. Next is, if you have CH3C triple bond C minus, you could notice that everything of these kind of questions, it's all same. Instead of this attack, we need to have C triple bond C, CH3. Here also C triple bond C, CH3. Okay, this is how it will get connected. But if the same question is now given in a different format where you have a protonation first, that means first we have taken acidic medium here. Okay. So if I take, let's say, H plus and then followed by H2, in that case, first you will get protonation like this. And this protonation is then followed by attack of water, right? And this time water attack will be on the more substitution kind. Yes. So what is the product you will get? You will get this as OH and two methyl groups with one OH group here. Done. This logic works the same irrespective of whatever nucleophile you take, except you need to have H plus and let's say MEOH. It is MEOH instead of simply OH here. Now we will have OMe. Now this as OMe. Okay. So it all depends upon what group you are using. That's it. Clear, everyone? Now, if you have HBr also, for example, if you have HBr also, the product is going to be the same. So first attack would be here, and instead of OH, now you must be attacking Br here. That's it. Okay. Plus charge here, plus here, and plus here. Everybody, please notice it. When you have two methyl groups, how to think. Done. Next, if you have even one phenyl group also, like this, instead of two, one phenyl group, it will still have the same ability. That is H plus and H2O. If you notice, the protonation will take place here. The protonation will take place here, and H2O will attack on this position only. That's how we will get end up OH and OH and phenyl. Okay, but when it is only one methyl, in that case, follow only normal SN2. Okay? Follow normal SN2. So which means first you'll make a protonation, H plus, then methanol to be added on this position by breaking this. What do I get? I'll get this as OH and methyl, sorry, OMe. OH and OMe. Yeah. Same logic, even if you have HBr here. So first protonation, H plus, and Br minus will attack on this same position, OH and Br. Okay. This is the addition when you have it on one bond only here. Got it? Next, if you have any questions based on this, it is like this. For example, if you have an epoxide here this way, and I'm treating that with PPH thrice. Obviously, here normal SN2 should happen. So what happens by normal SN2, we will get this as PPH thrice plus charge. This will become O minus and this way. And usually what happens is this O minus will again back attack on phosphorus. It will make a back attack on phosphorus. So we'll get this as phosphorus PH thrice connected with oxygen this way. Okay, clear? And this will make into a double bond formation, and we will get alkene here with PH thrice P double bond O. This is the product form. Okay, and same logic here also. Suppose if you have epoxide here and two methyl groups are on the same side, methyl and methyl are on the same side here, then you use PPH thrice. Then because it is like an anti-elimination, this is like an anti-elimination. So erythro with anti-elimination will give you trans. And if you have one methyl and the other methyl is going inside like this, and then if you have PPH thrice, which is also an anti-elimination, then you will get this as cis. Get this as cis. Okay, so this is the form you will observe. Everybody got that? Right, guys, that's it. This is how much we need to know from ethers. Correct. Mostly from ethers, if anything is asked, that is from this page only. This is page number 10. If you notice, this is the area which you need to revise properly. Okay, in which case, what to take. Okay. Other than that, Zichel's method, and yeah, this one, cleavage in concentrated HI. How does it happen? Okay. Hydrolysis, how does that happen? We have discussed it before, but I would suggest go through it once again. What happens on hydrolysis cases also? Okay, in which side it will go? Okay, that's it. That is all you need to know it from this topic. So we'll do one thing. We'll stop it here, and